Okay, thank you very much for allowing me to speak here today. It's really a pleasure. So, as announced, I was speaking about Fourier Mukai partner of canonical covers in positive characteristics. This is a joint work with Katrina Honigs, somewhere in this audience. Say hi to Katrina, and to Luigi Lombardi, somewhere in New York State. So, so not in this audience. So, okay, so more or less I will split this talk in 3 parts. In the first one, I will speak about motivation / background. In the second part, I will speak about complex surfaces. And in the third one, I explain the main result. And I will try, if I have time, to bore you with the proofs. Okay, so let's start with part 1, motivation and background. Okay, so let X be a smooth projective variety over K, algebraically closed, and the characteristic of K will always be different from 2. And at a certain point, it will be also different from 3. So, attached to X, we have the derived category of coherent sheaf of X, so the bounded derived category of coherent sheaf. Whose object are asymptotically vanishing complex of sheaves with coherent cohomology and up to quasi-isomorphism. Okay, so now I have to. So the morphisms in this category are a little more complicated. You don't really want to know, but since we are here, so the morphisms between 2 complexes are given by roofs of this kind, where this is a quasi-isomorphism and this is a morphism in the category of complexes. And since we want everything to compose in a fine manner, we quotient everything but a horrible equivalence relation. Okay, so this category is not abelian, but is exact, meaning it's triangulated, meaning that it's equipped with distinguished triangles, so that are triplets of object and triplets of morphism. And we say that a functor from a triangulated category to another triangulated category is exact if it sends distinguished triangles in distinguished triangles. So we have a notion of exact functor. Oh, and so this is a shift. So these are complexes. So this is a shift of one's place to the left. And it's an exact functor that's also to commute with the shift factor. So the definition is if we say that x and y, where y is again smooth projective over k, are D equivalent or Fourier Mukai partners or FM partners in brief, if exists an exact equivalence phi from between their bounded derived category of coherent shift. Okay, it's a well-known result. No, I don't need to erase. So it's a well-known result of Gabriel. No, wrong. So, okay, I'm already lost with the blackboard. Then I have to put this down and I clearly overdid it. So a little. So the main question is what geometric information does dBx carry? So it's a well-known result of Gabriel that two smooth projective variety, which have the same abelian category of coherent shift, are indeed isomorphic. And this is also true for algebraic space. It's a recent result of John Calabrese and Grothendieck, that sound like Grothendieck, but is not Grothendieck. So what about dBx? And there are two answers. So the first answer is a lot, meaning that Fourier Mukai partner have the same dimension, the same Kodaira dimension, the same canonical ring, the same order of the canonical bundle, and there is also a theorem of Poppa, Schnell, and Honigs for the characteristics. So Poppa and Schnell is complex, and Honigs is for positive characteristic. They say that Fourier Mukai partners have isogenous Albanese variety, there is...
Over an algebraically closed field.
Yes, but is algebraically closed.
Okay, sorry.
So, yeah. And over non-algebraically closed field, like it's... if you have more arithmetics flavor, so I lied at the beginning, but if surface and abelian varieties over a really not algebraically closed field have the same, which are the equivalent have the same zeta function. And also, it's hold for threefold up to base change, so for f, q, n for some n. So threefold. So the equivalent threefold have the same zeta function after base change with some f, q, n. So there is a wide variety. There is something for every flavor, like from complex to arithmetic. There are many properties that are preserved by a Fourier Mukai equivalence. And so the second answer to the question is, but not everything. So there is a famous example of Mukai in 1981, in which if you take A, an abelian variety, and A hat, it's dual, and you take the Poincaré bundle on A hat, A times E hat, then you can create this function, this functor between dBA in dBA hat. So you basically use the same formula for the Fourier transform in analysis. So that is why it's Fourier Mukai transform. So you have an object in dBAA, you pull it back to the product, you tensor by the exponential of E. So you have a function in X, you tensor for the exponential of E to the EXC, and then you integrate the X variable. So you get rid of the X variable. And this gives you an equivalence here. But now if you take an abelian variety that is not principal polarizable, then A hat will not be isomorphic to A. And so you have an example of two non-isomorphic variety with the same derived category. So at this point, the question is, if we pick a variety, can we say if there are Fourier Mukai partners, non-trivial Fourier Mukai partners, or can we count them? And for the case of complex surface, so this brings to the second part of the talk, that is a case of the case of complex surfaces. So Bridgeland and Machocha in 1988 proved that if X is a smooth projective surface over C, and Y is a Fourier-Mukai partner of X, then Y is isomorphic to X unless Y, so, okay, X and so Y is abelian. Two, X and so Y is K3. 3, X, and so Y is elliptic of Kodaira dimension 1. And in any case, Y is isomorphic to a moduli space of sheaves of like stable sheaves on X. So we have a really clear description of modular space of derived Fourier-Mukai partner of complex surface. So, okay, no, wrong one. So okay, I should put down this one. I think is the and we have also more, like it's, okay, so we can, there are some special abelian surface or special K3 surface. Like for example, there are K3 surface with large Picard number, and it has been proved thanks to the result of Nikulin that complex surface with Picard lattice of rank bigger than 12, then have bigger or equal to 12 and non-trivial Fourier-Mukai partners. And other special case are abelian surface that lie above bielliptic surface, or K3 surface that lie above Enriques surface. And there is this theorem of Sosna, don't remember the year, I'm sorry, that it shows that abelian surface and K3 surfaces arising as canonical covers of bielliptic and Enriques surface do not have any non-trivial Fourier Mukai partner. Meaning that an equivalence of the derived category of a surface like that with something else, it induces an isomorphism. Like not it induces, it's yelled that the two things are isomorphic. So a little remark on how the proof of this theorem goes in over the complex number. So usually you have a statement, like the derived equivalence implies a statement at the level of Hodge cohomology. And then you plug into the Hodge theory box, and it performs a miracle known as Torelli theorem most of the time, and you have the proof. So, of course, if you want to discuss this kind of problem in characteristic P, there is a problem. So there is not an immediate translation of this problem in characteristic P. And one of the pioneering results in characteristic P, that was the one that gave us the idea of starting this project, is okay, so this should be okay. Is a theorem of Lieblich and Olson, I would say 2011, 2016, like the first version is 2011, the last version that has to appear, so I don't think there will be new version is 2016, say that if like x over k equal k bar and characteristic different from 2, a K3 surface, and y do equivalent to x, then y is a K3 surface, and y is isomorphic to some moduli space of sheaves, like stable sheaves on X. So it's not possible to miss the similarity between this setting and Bridgeland setting. And so we ask ourselves, what about Sosna theorem? Like, what about abelian variety first? And what about Sosna theorem? And so we go to the third part. The third part is, this is results, in which we prove, so this is Honigs. Any question? No. Lombardi and myself. We showed that first, if char k different than 2, and also always algebraically close, x K3 surface covering, like, that is the canonical cover of an Enriques then X has no non-trivial F and partners. And 2, so now I am in trouble, I think. If the characteristic of the ground field is different from 3, and X is an abelian surface that is the canonical cover of a bielliptic surface, then X has no non-trivial Fourier Mukai partner. Okay, so I have 20 minutes to bore you with the proofs. So, and I am afraid that many of you will find them a bit dissatisfying because we cheat, like we lift to characteristic 0. So, but yeah. We don't know. So the thing is, if the characteristic of 2 is, okay, so in the first case, if the characteristic of is 2, then you're not sure you have a K3 surface, but you have a K3-like surface that you know to be Gorenstein, but you know also to be, so there are some cases in which it has bad singularities. So, and here, we don't know. We haven't thought about. So for K3s for like characteristic 2 is bad for my point of view, but so there is not much known. Like for example, okay, so we know that the derived category recognizes the 3 kind of Enriques surface in characteristic 2, but I would not know how to prove anything. So, but it is in my long list to do, but we will see. So it's, the answer is, here it has to be reformulated in some way, and here I don't know. I think it should hold in characteristic, at least in characteristic 3. Characteristic 2, I don't know, but characteristic 3, it should work. So, okay, so let's get to the proof. So the first step is proving this theorem that I will leave B for a moment, and again myself, that if this is an analogous of Liebling and also theorem for K3 surface. So if X is an abelian variety, and the characteristic of the ground field is different from 2, and Y is a Fourier Mukai partner of X, then Y is an abelian variety and Y is isomorphic to like a model. So this is a moduli space of sheaves on X, where these are the sheaves with the stable sheaf on X with Mukai vector V. Okay, so and also in the Liebling also, like it's moduli sheaf of X, so Y will be again the moduli space of stable sheaves on X with a given Mukai vector V. So V in both cases will be given by a rank, the class of a line bundle, and the Euler characteristic. So, no, in dimension 2, of course. It's. Oh, yes, surface. Sorry. Okay, so let's assume this for a moment. So what is the power of both Liebling-Olson theorem and of this theorem? It allowed to transform our problem to a lifting problem. So the idea, let's explain the lifting problem. So you have X and Y over K, and suppose you are able to deform X. So I'm using W improperly. It could be a ramified extension of the width vector. But so suppose you're able to deform X to characteristic 0, and you have here the geometric generic fiber. And suppose that you're also able to deform Y to characteristic 0, and you have the geometric generic fiber, and suppose that you can prove that these are the equivalent. One thing, so the theorem of Sosna and Bridgeland are stated over C, but they work over any algebraically closed field of characteristic 0 because the derived category is well behaved up to base extension. So there are no problems there. So, okay, suppose that here you have a derived equivalence, and suppose that you were so good that you know that the derived equivalence here implies an isomorphism here. Then you have that the two closed fibers are birationally equivalent, but if X is K3 or an abelian variety, you have an isomorphism there. So the trick is try to deform. So you have to deform X such that the geometric generic fiber has no non-trivial Fourier Mukai partner, and deform Y in such a way that the geometric generic fiber of Y is the equivalent to X. And of course, you cannot do it randomly, like you choose a deformation of X and a deformation of Y and hope that everything works. Because you can, so think that X is a product of elliptic curve. You can deform these as a product of the elliptic curve, but you could also deform that as a simple variety, abelian variety, and this could not be the equivalent. And so it's really important to keep track of the whole thing. And this theorem and Liebig also theorem is what all of us, because now, let me use colored chalk. I hope there are no colorblind in this room. But, so if this is a moduli space of sheaf of X, suppose that, so V is given by a rank, a first Chern class, and an Euler characteristic. Suppose that you can deform X along with X, then you have a good candidate for, so like L tilde, for your deformation of Y. Now you have a problem, because even if here, so here, when you do this stuff, you know that there is a universal family, and these are going to be the equivalent. So you have to have also a universal, like, so these will become M xk R L tilde restricted to K chi. So here, you don't know a priori if you have an universal family. So the way in which you know, it's usually here you have another Mukai vector such that L dot L prime minus R prime chi minus R chi prime is equal 1. This is a condition for having a universal family here, and it's a condition for having a universal family here. So a good way to have a universal family would be to lift also L prime tilde. Okay, so think if this is a product of elliptic curve. So Sosna proved slightly more than what I say. So he goes through Bagnera de Franchi's table, and he sees that anything that has the possible form of an abelian variety line on a K3 surface, on a bielliptic surface, is has non-trivial Fourier Mukai partner. Okay, suppose now you have E times F. So you think, okay, I want to use Sosna result, and I lift E, and I lift F. And I make their product. This is a lifting, and I can do this. But then in order to do this, I have to, so this is a two-dimensional deformation space. Now I'm lifting a line bundle, one-dimensional deformation space. Now I'm lifting another line bundle. Oh, maybe I'm not deforming. And the trick is that, so we just are assuming that there is an equivalence, but we can modify our equivalence. We can, so in this case, we can compose with the Fourier Mukai transform with the induced by the canonical bundle, the Poincaré bundle, and so it's this this transforms this vector by swapping the rank and the Euler characteristic and putting using the Poincaré dual here. And you can tensor for a line bundle. There is many things you can do. And by using many times the Chinese remainder theorem, we manage to get a transform in this particular case in which R and chi are relatively prime. So this is 0. You can take this to be 0, and you don't have to lift it. And so in this particular case, we manage to solve it. All the other are modifications. So all the other for the abelian variety are modification of these, because we use that there is either a 2-to-1 or a 3-to-1 cover like that, and so there is also map in the other direction. And by playing like that, we manage to show that the lift here come from something that we can lift here. Okay, one thing I have not discussed is, so it's not true that, so it's still I'm moving on a one-dimensional space. I have to see if this is still possible, if it's not obstructed, and I can really lift this given line bundle. And the answer is yes. So how we lift, so we use the description of our line bundle on the product of the elliptic curve. So L will be the class of a line bundle, and L, since it's on the product of two elliptic curves, and L so will be equal something like D and tensor D1 O Q upper star OF of D2. So line bundle on the product of the elliptic curve can always be described by two line bundle on the elliptic curve and an isogeny between the two. By working with, composing with autoequivalence, we can always assume that this is separable. When it's ordinary, we just use, this is a canonical cover. So the thing is, when E and F are both ordinary, this is a canonical lift. And there is no problem in lifting line bundle to the canonical lift. So E and F, one is ordinary and the other is not. There is no this part. There are no isogenies between the two. And so we lift the line bundle by simply lifting this line bundle on the first curve and lifting the other bundle on the second curve. There are no obstruction to lift line bundle in curves. So if they're both super singular, then by working around, we can assume that this is separable. And what we do is we lift one of the, so phi is here, so it should go from, there is a 50% of chance I made it wrong, but, so in this case, we find a lift of F. Phi is separable, so is a tal. We lift the tal cover, and the Mumford bundle, this is a Poincaré bundle, always lift. And so we can lift this part, and then we lift this two-line bundle. So we managed to always solve this lifting problem of a product of two elliptic curve of one of Bagnera de Franchi and a line bundle, and everything work for the abelian surface. The K3 surface is easier because what I have not said is that Liebringen also proved that supersingular K3 surface have no non-singular Fourier Mukai, no non-trivial Fourier Mukai partner. So we can assume X to be ordinary. And so since Shada supersingular and RT supersingular are proved now to be equivalent, we can show that these as finite 8. So there is a Néron preserving lift. And so if K3 that lie above Enriques, ordinary K3 that lie above Enriques, are identified by the Néron-Severi. That is equal to the Néron-Severi here. So the same result tells you that this is a K3 that lie above an Enriques, and then you use Sosna result and everything work. And you can lift the line bundle because it's a Néron-Severi preserving lift. And so you are done. So yeah, I think I will stop here, not bother you with proof of theorem 2.